Good morning. Welcome to class. It is Thursday, April 30th. Um, it's my wife's birthday. If any of you want to say happy birthday to her, um, we only accept gifts in cash, so send me all of your money right now. Um, so today we're just going to finish up our series parallel classwork. I can answer some questions on the homework if you have them. After I go through this, I'm going to post the review for your test, which will be next week. So you'll have the review. I haven't posted the answers yet. I'll probably post those Monday next week or something like that. And that'll be the classes looking at the review and then mostly answering your questions. I don't intend to work through all of it. I want you to try to work through it and ask me questions, and I can help you with specific questions. So that's the goal for Monday, is that hopefully you've worked through the review, and then I can help you with specific questions you have. And then, I'll post the test, and that's mostly it for the year. I'm going to go through a little bit of magnetism just because I like magnetism, and I have things built that can show you magnetism. All right, so let's get to it. All we have left is number 3 on the classwork. And number 3 is the most complicated circuit we've seen so far. I'm not going to ask you a more complicated circuit than this unless it's a bonus question. So here we have a diagram. We have 5 identical 20 ohm resistors. So each of these resistors is 20 ohms, and it's in a combination of series and parallel. So kind of be thinking which of these are in parallel, which are in series, and some of these are in series with each other, but not in series with the total circuit. So try to be thinking which of these are in series, which are in parallel. They're connected to a 4-volt voltage source. So this right here is 4 volts. So A wants to know which resistor or resistors receive the most current. Explain. So I'm going to draw this out. It might be helpful for you to draw it out, or if you printed it, then that'll be helpful. So I have a resistor here, and then we split up here. We have resistor 1, 2, 3, 4, 5. All of these are 20 ohm resistors. I have a 4-volt battery. All right, so current. Current is the amount of electrons flowing per time, so amount of charge. Again, back to charge not being created or destroyed. So what are some guesses on which one of these are going to get a lot of current? So which of these resistors are in series? Which of these have to have the current going through them? So current is the amount of charge. So when I get to a point here, I have a point here, the current has to decide, is it going to go up or is it going to go down? A single electron can only go up here or down here. So when I get to a parallel, my current is going to split up. Some is going to go here and here. But whenever I'm looking in series, all of that current has to go through series. So every single electron has to go through resistor 1, and every single electron has to go through resistor 5, right? But then the electrons get up here, and they can choose some will go up here, some will go down here. So parallel, they're going to get the full voltage. So we can make that chart real fast. So series, we're going to split voltage, and they get the full current. And then in parallel, they're going to split the current and get the full voltage. So I send out electrons this way. My total current goes through resistor 1, And then current is made up of electrons. Electrons aren't being created or destroyed. Some of my current has to go down, and some of my current has to go up. So I'm going to just current up, current down. I don't know, I'm not very creative. Then the current goes along here, and then the current recombines, right? All of the electrons go up or down. Electrons aren't being destroyed. They're not poofing into existence. So all of those electrons recombine here. So what can I say about the amount of current leaving this total parallel branch versus the amount of current going in? Yeah, it's equal to how much went in. Yeah, so if it adds back up to the same before. So the current splits up and then recombines to be equal to my total current. So the total current goes through 5, and then all of that current returns to the battery. So Holly was right. 1 and 5 get that entire current. So for A, so 1 and 5 get the most current. Yeah, they get the most current and they get the equal current. And then we can kind of think, which one of these is going to get more current? I know it doesn't ask that on here, but this is easily a question I could ask you. Out of 2, 3, and 4, which of those gets more current? Which path is easier to go through? Especially with identical resistors. So looking at that, I can go up. If I go up here, I have to go through 2 and 3. If I go down here, I only have to go through 4. So 4 is easier to go through. This is only 20 ohms. Here I have two 20 ohm resistors, so this is going to be 40 ohms. So back to our grocery store analogy, everyone has to go through this checkout line, and then I could go up here and go through 2 of the same checkout lines, or I could just go to 1 of the checkout lines. So more people are going to want to go through just the 1 checkout line. Now, eventually in a store, the line is going to back up so much that people are going to get to the point where it's like, well, it's going to take a long time waiting in this line, so it might take less time just to go through here. So it's not quite a short circuit. More people are going to go here, but eventually this line will back up so long that it would take less time to get through these 2 lines than to wait for everyone to get through this line. So not quite a short circuit. More circuit goes down here, less goes up here. So this current down is going to have more current than the current up. So the current down is going to be bigger than the current going through that top path. Yeah, if you have to go through the 2 lines, that takes longer, but eventually, so let's imagine a scenario where every single person tries to go through this line. If everyone tries to go through this line, the line is going to back up a really long amount. And then eventually this person way back here is going to decide, hey, it's going to be faster to go through these 2 lines than to wait for everyone to go through this line. And so eventually someone's going to get fed up and then decide to go through the 2 lines. So, or just shop online. Yeah, I mean, electrons don't have the chance to shop online. So we could rank this even further down. So then 4 would get the next most current, and then 2 and 3 would get the least current. And because these are in series with each other, these will get the same amount of current. All electrons that go through 2 also go through 3. So 2 and 3 get the same current, and they're the absolute least. So we could, drawing it is really helpful. I would suggest drawing this. So we could rank current. So current 1 and 5 are the most. And then the next most, 4. And then the least amount of current are going to be 2 and 3. An electron online shopping. Yeah, see the electron online shopping, but then you have all of the electrons working in the warehouse. And so you would have to draw the electrons going through the warehouse. You're just shifting around where the lines are happening. So you have all of those electrons in the warehouses getting electron COVID-19. All right, so we already kind of answered our question, which get the least amount of current. You have to wait a bit. So yeah, I mean, so that would be another resistor. I mean, if we're extending this analogy like even further, then yeah, the transport would be a resistor. So 2 and 3 get less current. And by the way, whenever they were thinking of currents and voltages and everything, they were relating this to like pipes, like water going through a pipe into your house, things like that. And that's why they use the word current, like water current versus electron current. And they didn't even know what electrons were. But you wouldn't have to you have to get out of bed to open the door. That's the resistance, is opening the door. But yeah, that's why a lot of these work really well with analogies of flow. They were imagining this like water flowing through a pipe, which works really well to an extent. All right, now C now wants us to find values for an entire circuit. So 1 wants us to get our total resistance. So looking through our circuit, let's try to find things that are most simply connected. So let's try to find 2 resistors that are in simple series or 2 resistors that are in simple parallel. So out of these, which 2 resistors would be easiest to combine to 1 resistor? Well, starting out here, we have 1 and 5 are in series. So 1 and 5 in series. In series, we just add the resistances, right? So resistance 1 plus resistance 5 is equal to 20 plus 20 equals 40 ohms. So I could imagine resistance 1 and 5 as a single resistor. So let's draw that out. So instead of drawing 2 resistors there, I have resistor 1 and 5 is a 40 ohm resistor, my equivalent resistance or total resistance, and then ignore the resistor down here. What are the other 2 resistors that are in simple series? It doesn't look super fuzzy to me. Sometimes it gets like that, where the camera goes fuzzy for a bit. But the other 2 that are in simple series are 2 and 3, right? See, 2 and 3 are in series with each other. They're not in series with the battery, but they're in series with each other. So I could just pretend like this is 1 resistor up here. So I have a 20 ohm resistor and a 20 ohm resistor. So I could imagine this is just resistor 2 and 3 are like a big 40 ohm resistor. And then I still have this resistor down here. Resistor 4 by itself is still a 20 ohm resistor. And then these combine back together. So yeah, sometimes I think it's just like a bandwidth issue. Like it tries to record so much and I might move a lot, and then it lowers the quality of the video in order to get it through faster. All right, so questions on this? Right, see how we found these 2 are in parallel with each other, these 2 are in parallel with each other, and we were able to combine those into 1. Now, out of these, what are the 2 that we can combine together? Which are in simple series or parallel with each other? So we have parallel. We have these two that are now in simple parallel with each other. Now, adding in parallel, we add the inverses, right? So that 1 over the total resistance for that parallel branch is going to be 1 over that 40 ohm resistor plus 1 over the 20 ohm resistor. Again, let's not forget we have to flip our answer after we get it. -1. So the parallel resistance, 1/20th plus 1/40th. Well, that's the same as 1/40th plus 2/40ths, which would be 3/40ths. And then you flip that over, 40 divided by 3. So you should get 13.333 ohms, I think, right? Yeah, 13.333. Yeah, and I'm going to redraw this, especially when we're doing these like much more complicated combinations of resistors. It might be nice to redraw each steps. It's a big pain. It's annoying, but I know a lot of people struggle with keeping these together. So we have this 40 ohm resistor here, and now instead of this parallel branch, it's like we have a single 13.33 ohm resistor. And then yeah, now I have these in simple series, and we can just, like you said, Vincent, add this to this. So that total resistance in series, I just add the values, 40 plus 13.333 ohms. So my total resistance for the entire circuit is going to be 53.333, repeating indefinitely, ohms. So start with the like resistors. I saw 1 and 5 are in series with each other, 2 and 3 in series with each other. So I added 1 and 5 together to make 1 resistor. I added 2 and 3 together to make 1 resistor. Now all of a sudden I had a series, only 1, but I had 2 in simple parallel. So now I could add these together in parallel, adding the inverses. One of the biggest things, remember you have to invert your answer after you add your 2 fractions. Otherwise, you won't get the right answer. So then once we did it, we combined this into a single resistor. And so we just now had 2 in series that we can just simply add. Yeah, you can rewatch it whenever. Yeah, that actually is probably the amount of people on the Wi-Fi. Yeah, that definitely sounds like a bandwidth issue. So total resistance is usually going to be the harder one to find. Because total current, we can just use Ohm's law. Total voltage equals total current times total resistance. I can divide resistance over, so total current equals total voltage divided by total resistance. We have a 4-volt battery, 53.333 ohms of total resistance. And if you add enough 3's in there, or you put it as a fraction, you should get 0.075 amps. Or 75 milliamps, if you want to put it in milliamps. Yeah, sometimes even with an Ethernet, depending on, I guess it depends on what your bandwidth is. I would imagine if people are trying to watch a lot of HD video all at once, if you don't have the biggest, most bandwidth for internet, it can probably start being an issue. Yeah, there's a reason I have the router in my room. So I have, like, my media computer is directly connected by Ethernet, and then my gaming computer is connected by 5G. Not 5, the 5 gigawatt signal. No, gigahertz. Jeez, I should know this physics. Because yeah, the 5 gigahertz, you can get a better signal, but it's more short range due to diffraction. But an SSD, that's actually pretty terrible. Why couldn't you use the SSD? You should be able to connect to you should be able to connect as many hard drives as you want. Um, Sometimes I just have like hard drives free floating in my computer. Like if I like shake it around, you'll hear the hard drive sliding around. But you should have more slots into your motherboard. You might not be able to use the fastest slot for that solid state drive, so it might be a little bit slower than your main one. All right, power. So total power is current times voltage. Now again, there are going to be some times that we see on our review where it's really good to use power as voltage squared over resistance, or power is current squared times voltage, especially when we're trying to describe individual resistors. We're going to use these in a second also. So power, we have a total current of 0.075 amps. We have a total voltage of 4 volts. 75 times 4 should be 3. So what, you get 0.3, I think. Yep, 0.3 watts. All right, now we need to find our values through each individual resistor. So this one, I'm not necessarily going to do it completely in order. I'm going to start this on a whole other page. And I'm even going to redraw this. That might be helpful. Actually, no, I drew it big enough right here. All right, so we want to get current, voltage drop, and power for each individual resistor. So starting with current, which one of these do we already know the current for? Which of these resistors get the entire current for the circuit? Yeah, 1 and 5 are in series with the battery, so these get our total current because these are in simple series. So these get the entire current going through the circuit. So current 1 is equal to that entire 0.075 amps. And current 2 is equal to that entire, not 2, current 5 is equal to that entire 0.075 amps. So we know a little bit more about 1 and 5. So let's kind of jump down here to part 2. So for part 2, we're trying to find the voltage drop for the resistors. So voltage drop, that's just going to be using Ohm's law, right? Voltage drop is going to equal current times resistance, V equals IR, Ohm's law. So I could do that voltage drop for 1. So voltage drop for 1 is going to be current through resistor 1 times resistance 1. So this gets the entire 0.075 amps, and it's a 20 ohm resistor. And if we notice for 5 also gets that entire 0.075 amps, and it's an identical resistor, 20 ohm resistor. So 1 and 5 are going to take the same voltage drop also, by coincidence. So voltage drop across 1, voltage drop across 2. 75 times 2 is 150. But 0.075, we go up by 1, so we get 0.15. 0.15 volts. 0.15 volts. Wait, no. 1.5, right? 1.5. Should be that. Check my math. (20 times 0.075). Yeah, 1.5 volts. So we see here, we had 4 volts, but these are in series, so they have to split up that voltage. So 1 took up 1.5 of the volts, 5 took up 1.5 of the volts. Let's kind of look at this. We went through our battery. After I get through my battery, I have 4 volts. When I return to my battery, I have 0 volts. Across resistor 1, I lose 1.5 volts. So by the time I get here, 4 minus 1.5, I have 2.5 volts. Now, across resistor 5, I lost 1.5 volts. This used up 1.5 of the volts. Again, voltage you can think kind of in terms of energy. Voltage is very similar to energy. It's not exactly the same. All right, so I lost 1.5 volts here. I end up at 0. That means I had to be at 1.5 volts before I got to that resistor, right? 1.5 volts, and then I lose 1.5 volts, so I go down to 0 volts. So that means on the other side right here of my parallel branch, I have 1.5 volts. So which of these resistors is it going to be easier to get the voltage for? 2 and 3 or 4? So notice here, what's my voltage drop across this entire branch? How much do I go from here to here? Yeah, I drop by 1 volt across that entire branch. But looking at this one, 4 is the only individual resistor here. So I could say when I go through this resistor, I lose 1 volt, right? So to go from 2.5 volts down to 1.5 volts, I have to lose 1 volt here, right? Because right here, I'm also at 2.5 volts, going down to 1.5 volts. 2.5 volts down to 1.5 volts. Again, the only time I lose voltage is across resistor. So I lose a volt across resistor 4. So that gives me one answer. I can put that in here. The voltage drop across 4 is going to be 1 volt. And again, based on what we're saying, I really should put voltage drop as my subscript. The change in voltage across resistor 4 is -1. The voltage drop is 1. Yeah, so very good. So we see that 2 and 3 are in series. That means in series they're going to have to split up the voltage. They're identical resistors, so we expect each one of these to lose half a volt, right? There's 1 volt across this entire thing, so we expect each of these to lose 0.5 volts. Let's try to go through and figure this out mathematically, though. Because if we figure this out mathematically, then we can prove that as opposed to assuming it. And a lot of times we're not going to have identical resistors where you can do something as simple as that. So you are 100% correct. It is going to be half a volt across each, but let's actually go and try to figure that out. So now I know the voltage drop across 4. I can use that voltage drop to get current, right? voltage equals current times resistance. So current through resistor 4, divide resistance over, is going to be the voltage drop across 4 divided by resistance of resistor 4. So I have 1 volt drop across resistor 4. It's a 20 ohm resistor. 1/20th is 0.05. Yeah, 0.05. Right next to it. So current through resistor 5 is that's 4.05 amps. Now I can kind of look at resistor 2 and 3 as a single resistor, right? So the voltage drop across resistor 2 and 3 as a whole is going to be the current through resistor 2 and 3 as a whole times the resistance of resistor 2 and 3. So we can see the current through resistors 2 and 3, which is going to be the same, right? Because these are in series. All electrons that go through 2 have to also go through 3. So this is going to be voltage divided by resistance. So these also get 1 volt across both of them. But they have a total resistance here and here of 40, right? I have to go through the 20 and the other 20. So that total resistance is going to be 40 ohms in series. Right, these get 1 volt equals the current through 2 and 3. And then we see resistance of 2 and 3 is just going to be 20 plus 20 ohms. So 1 divided by 40 is 1/4 is 0.25 divided by 10, 0.025. So the current through resistor 2 is going to equal the current through resistor 3 because they're in series with each other. Not in series with the battery, so they don't get the entire current from the battery, but they're in series with each other, so they get the same current. These get that 0.025 amps. And again, for my drawing up here, I called this my current up, and I called this my current down. And we should see they split up into 0.05 and 0.025. But if I add these up, the current down plus the current up, 0.05 plus 0.025, I end up getting 0.075 amps. So 0.05 go down, 0.025 go up, but I still have a total of 0.075 amps. So even though these are splitting up, I still have the same amount of electrons. So at every time, I still have the same number of electrons. So now I can go down here. Now I know my current through 2, 3, and 4. I can get my voltage drop. Well, I just need for 2 and 3. So voltage drop for resistor 2 is going to be the current through resistor 2 times the resistance of resistor 2. Voltage drop through resistor 3 is going to be current through resistor 3 times resistance of resistor 3. So these both get that 0.025 amps of current. And by the way, the other way of seeing this is I have twice the resistance up here as I do down here. So this gets half the current that gets. So you can do simple ratios if you get really good at this. So 20 ohms. This also has 0.025 amps, and it's an identical resistor, 20 ohms. And yeah, 0.025 times 10 is 0.25 times 2 is 0.5. So we get a voltage drop across 2 is 0.5 volts. Voltage drop across 3 is 0.5 volts. And just by kind of guessing, they're identical resistors, so they would each take up half of that 1 volt dropped across them. So we lose minus 0.5 volts. You can see, I mean, I hope you can see. I think you mean you can see the paper. We're down to 0.5 volt. No, we're down. What am I doing? We lost half a volt. We were at 2.5 volts, so we're at 2 volts here. And then we lost the other 0.5 volt here. So 2 minus 0.5, we're down to 1.5 volts. Lot going on there, right? I'm probably not going to ask you to solve for every single one of these on the test. Well, I mean, I guarantee I'm not going to ask you to solve for every single one of these on the test. That would be a nightmare to grade. But I could ask for any individual one of these is the tricky thing. All right, so part 3, we can solve for power. Now, normally I don't give all of these equations for power on a test, but obviously I can't make you take this as a non-open note test. That would just be stupid of me to think that would be possible. But let's look at when these equations would be the most useful. Power equals current times voltage, power equals voltage squared divided by resistance, and power equals current squared times resistance. Now, you don't like slope forces. Yeah, it's not so bad. You just either take the area or slope. You're doing y divided by x or y times x. You can also do that with currents. You can use Ohm's law pretty easily on a graph where we would have, where we could graph, say, because current is voltage divided by resistance, we could put voltage on the y-axis, resistance on the x-axis, and take the slope to get current. That's a thing I would make you do in a lab if we were at school. All right, so we could use any of these. Now, most of the time we're given resistances. So most of the time we're given resistances. So we're given R. So we probably want to use one of these two equations. So a lot of times this is actually going to be one of the harder equations to use. Now, we have two different cases. In series, both objects get the full current. And so because they get the full current, I know resistance, I know current. So in series, we're probably going to want to use the power with current and resistance. Power equals current squared times resistance. This is going to be the one where I need to do the least amount of finding things and before I can use my power equation. In parallel, the resistors get the full voltage. That means voltage is going to be the easiest thing to find. So I'm given resistance, I know voltage, so I probably want to use the power equation with voltage and resistance. So I'm probably going to use power equals voltage squared divided by resistance. Now, it doesn't matter so much for what we've done. We've already solved everything to this point. I could easily just do current times voltage for all of these. But again, I guarantee on your review and on your tests, there's going to be ones where you could go through and solve everything, but that's going to be way more than you have to solve for. So everything in series, I want to use power as current squared times resistance. Everything in parallel, voltage squared divided by resistance. So the series ones, that's going to be power through 1 is going to be currents through 1 squared times resistance of resistor 1. Well, 1 gets that full current, 0.075 amps. And notice current was that first thing we were able to solve for. That's what's nice about this. I solved for this really fast, and then I could just multiply it by that resistance of 20 ohms. So I could have found this power at the very beginning as opposed to having to go through here, figure out the voltage, then do this times this. It's just a little bit quicker. And I am lazy. Work smarter, not harder. We get the power by resistor 1 is 0.1125 watts. Then resistor 5, again, is in series, resistance through 5, the numbers are identical for resistor 5, right? Same resistor, same current. It's getting that total current from the circuit. So power through resistor 5 is also going to be 0.1125 watts. All right, then we get to the next one. So now we're going to have to look at our parallel resistors. Well, in parallel, it's resistor 4 was a little bit easier to find, right? We had to go through a little bit more to get to here, but 4 was more straightforward. 4, it was easier to get my voltage. Notice I got the voltage of 4 before I went to solve for current. So because I got the voltage more easily, that's why I want to use my voltage squared over resistance. I already know my resistance. Voltage was easier to find than current. So that's why we want to try to use this one. You don't have to. It's just, again, laziness is nice. Because again, that's the whole point of physics, is being lazy and getting the correct answer. So you just have to know how to be lazy. 1 volt squared. We have a resistor of 20 ohms. 1 divided by 20 is 0.05. 0.05 watts. And then the hardest two to get noted by the last two that we solved were for 2 and 3. Now, 2 and 3 is where we're kind of, it's in series and in parallel. So we can kind of look at which one was easier to find. Well, notice we went through and we solved for our current first. Current was a little bit easier to get through that branch than it was to get our voltage drop. So we're probably going to want to use our equation with current. So even though it's in series and in parallel, it was easier to solve for the series part first. And because we solved for the series current first, we probably want to use the current squared times resistance. Again, that way we solve for this without having to do the additional step of finding the voltages. There's nothing wrong with that. It's just easier, faster. The other thing is, just some point in your life, you might have to write some sort of code or something that has to do a lot of equations, and just simply cutting out a step that the code has to execute, especially if you're doing this like thousands or hundreds of thousands or millions of times, you could actually save large sums of money based on the amount of computing time you saved. Not that you're all going to do that, but just something that can happen. 0.025 amps squared times 20 ohm resistor, identical resistors, so this is going to look the same. .25 squared, 625, but that's 0.0016. Yeah, I'm just going to put this in the calculator. So power through 2 and the power through 3 are both 0.0125 watts. And I will say, one thing I am going to ask you to do is you definitely have a series parallel circuit on your test, and you definitely have to say which light bulb is going to be the brightest. And so we're going to see here, a lot of times in series parallel, the two that are in simple series are brighter. But your test is randomized, again, based on your student ID. And so it won't always work that way if you have different resistors. But we would see these two, most power, these two are going to be the most bright. These two have the least power because they have to split the current. Some current goes up, some goes down. They split the current and they split the voltage with each other. So they have all the downsides of being in parallel and the downsides of being in series. So they just got like really little. They just got the little leftover scraps of everything, and they have this tiny amount of power. So exactly 10 times less than 1 and 5 got. And then these are the resistor 4 is pretty close to in the middle of this, so it's I don't know, how would you describe that? Medium brightness. And in reality, there's a good chance these two just wouldn't light up. This one would just be like barely lit up, and these would be fully lit up. You shouldn't give up on coding. Just find some sort of coding language that's more straightforward. But figuring out how to do logic is really good for a lot of things. All right, so that was all of this one, because I don't code with like C++ or Java or Python really, but I do code in like Excel or Mathematica, dealing with math logic, just simple if then statements. Questions on this? So this is where things get hard, is where I'm asking find values for every individual resistor. This is where things get really complicated, and that's where most of the struggle is probably going to be on the test. Finding your totals normally aren't so bad. So if there's no other questions here, I'm going to stop the video now. I will post the review online right now. My plan is Monday I'm going to have class, but I don't have anything actually planned. I don't have like a warm-up. I don't have things that I have specifically to go through. I want you to show up and ask questions about the review. So the hope is that you've worked on the review today and tomorrow, maybe a little bit over the weekend, look at it before class Monday, show up and ask questions, and I can look at those. I'm probably also going to post the test. Actually, I'll probably post that on Wednesday. So yeah, that'll be that. And then that's pretty much it. We're right there at the end of the year. The week after that, I'm probably going to do just a little bit of magnetism, mostly just playing around and showing you things I built and just simple ideas behind magnetism, because magnetism is fun. Magnets are fun, except whenever they break boards. But yeah, other than that, just keep working, and I'll see you next class.